Howdy, students. This is going to be part 4 of our water unit that is going to cover solution formation. We're going to look at the factors that affect how solute dissolves in solvent, what speeds up that process, and then we're also going to look at solubility with gases, and then we're going to finish off by talking about Henry's law. So there are factors that affect the rate or the speed of solution. And the first one that we're going to talk about is agitation or stirring. And I think most of us have a good idea of this, but when we stir something, we bring fresh solvent in contact with more solute. It mixes it better. The salt comes into contact with the water or the sugar with the water, and we can dissolve things faster. It does not affect the amount of substances that actually dissolved. That is a term called solubility, and we're going to look at that in a little bit. So if we mix up some coffee, we can mix the creamer or the sugar inside there. Same thing with salt water or sugar water. The second factor that affects the speed of solution would be temperature. And once again, I think we have a good idea of this. If we heat up a solution, we increase the kinetic energy and the motion of the particles, and we can actually dissolve more solute within a solvent. So best example I can give you is tea. We brew it at hot temperatures, which allows us to dissolve lots and lots of sugar, which is where we get sweet tea. It's easier to dissolve sugar at a hot temperature than it is a cold temperature. So I don't know if you've ever had a glass of iced tea that's unsweetened at a restaurant, but if you try to dissolve the sugar in it, it doesn't work out so well. The third factor that affects the speed or the rate of solution is particle size. So particle size The third one is particle size. So the smaller the particles, they dissolve faster because of greater surface area. More solvent can actually contact more solute at one time. So if we have a large particle, the solvent has a defined surface area that it can get in contact with. But if we bust it up into smaller chunks, we have increased the surface area tremendously, and we can dissolve a lot faster. And again, I think you know this because if you dissolve sugar cubes in tea versus powdered sugar, the powdered sugar is going to dissolve a lot faster. So if we actually try to measure the amount of solute that dissolves in solvent, it's called solubility, which is a measure of the amount of solute that will dissolve in a given amount of solvent. So we're going to be looking at solubility charts that help us actually put a number on the amount of grams of solute that we can dissolve in a certain amount of solvent, which is usually water in most cases. And it's usually about 100 grams, and the solvent is usually water. So different substances have different solubilities: barium hydroxide, sodium chloride, and sucrose. We have temperature 1 here at 0 degrees, and temperature 2 at 20 degrees, and temperature 3 at 100 degrees. So what happens to barium hydroxide? Well, at 0 degrees Celsius, it can dissolve 1.67, and the units would be grams over 100 grams of water. At 20 degrees, we can dissolve about 30 grams more. And at 100 degrees, it doesn't look like we can dissolve any more. It stops. Solubility ceases. Table salt, we can dissolve 35.7. And again, this is grams over 100 grams of solvent. As you look, it only goes up about 1 gram and then 3 more grams at 100 degrees. So the solubility is very straightforward. Now, with barium hydroxide, it went up rapidly, but then it just kind of cut off. Sucrose goes 179 grams, 230, 487. So its solubility is very steep. So different substances have different solubilities. The last factor that affects solubility is actually, this is kind of our fourth one here. This is the nature of the solute in the solvent. And we talked about this earlier when we said that like dissolves like. So polar can dissolve ionic and polar. Nonpolar can dissolve nonpolar. So depending on what the substance is actually made of, it actually changes how much can be dissolved or not dissolved in something else. So with oil and water, there is 0 grams per 100 grams of solvent because they don't mix. They are immiscible. But if we have salt and water, then we actually have some sort of solubility. Like in the last slide, we saw that the solubility of salt at 0 degrees was 35.1 grams per 100 grams of water. Okay, temperature affects the actual amount of solubility. Most solids become more soluble at higher temperatures. A few become less soluble. So we're going to spend some time looking at these solubility charts and learning how to read them. On the y-axis, we have the solubility, which is the grams of your substance in 100 grams of H2O, which is very important to know. On the x-axis, we have temperature in degrees Celsius. And if we look, most of the compounds have an upward trajectory. Some are exponential, some are linear. But you'll notice that some substances are special, like cerium sulfate. It has a downward trend, which means as we heat it up, it actually lowers the solubility. So if we heated up this solution, we would have solid precipitating out from solution. The rest, if we heated it up, we would dissolve more. So if I had to ask you a question and say, KCl, what is the solubility at a temperature of 50 degrees Celsius? You would find KCl, you would find 50 degrees Celsius, travel up the line until you hit the right line right here, and then read over. And you would make a guess using the chart, and you would probably say somewhere around 42 grams for every 100 grams of H2O. That is our solubility. The solubility of gases are actually different from most ionic solids. So here, gases decrease in solubility as temperature increases. So you'll notice all gases, most of them, have downward trajectories. As you heat up gases, the solubility decreases. So if you think about it, what happens if you heat up soda? The kinetic energy in the gases is so great that they can't stay dissolved in the liquid form and they bubble out of solution. This is why your sodas go flat so fast if it's hot outside. Two different gases being compared here. Oxygen has a smaller slope. Carbon dioxide significantly reduces, and this is what's dissolved in your soda. So if we had oxygen dissolved in our sodas, as we heated up the temperature, it would not bubble out as much, but that's not what we do. But CO2, we lose a lot of gas as we heat up the temperature. Pressure can affect the solubility of gases and liquids. So again, we're focused on gases here in this slide. And we actually have an equation for this, and that's where we're going to finish this video. It's called Henry's Law. If we increase pressure from P1 to P2, we can actually dissolve more gas. And you'll notice that there are more gas particles dissolved in the liquid here. So if we increase the pressure, we increase the solubility. This is how we pressurize sodas. We have three terms to look at here: saturated solution, unsaturated, and supersaturated. And we're going to do a lab on Friday where we look at each one of these solutions. And what we're going to do is be able to demonstrate those three types of solutions. So a saturated solution contains the maximum amount of solute that will dissolve in a given amount of solvent at a given temperature. Unsaturated solution means that we have more solute that could be dissolved. It's indicated by no solid present. A supersaturated solution is when we have more solute dissolved than theoretically possible. So this is usually the hardest one for us to understand. But a saturated solution, we would dissolve the maximum amount, and what we would find is that we would actually have some stuff left at the bottom. Now, an unsaturated solution, we wouldn't see anything at the bottom because we have room. There is more room for us to dissolve. A supersaturated solution means that we have dissolved more than enough than theoretically possible. So with an unsaturated solution, we would dissolve the 30 grams of sodium chloride here. We would stir it up, and there's more room. With a saturated solution, we would dissolve 40 grams, and we would see some stuff left at the bottom. So if there's a solid present, it's a saturated solution. But if there's no solid present, we have two options, unsaturated or supersaturated. So to determine which is which, we're going to add a crystal. And we're going to see this in our lab on Friday. A supersaturated solution will actually crystallize out. An unsaturated solution would just continue dissolving. All right, so let's finish out with Henry's law here. At a given temperature, the solubility of a gas is directly proportional to the pressure of the gas above the liquid. So here's our equation. I would almost call this another gas law. S is for solubility. P is for pressure. The units of solubility are grams of salt over 100 grams of solvent. And the units of pressure can be kPa, mmHgs, torrs, psi, bars. We have lots of different conversions there. And then, of course, atmospheres. So just as a refresher, 101.3 kPa is equivalent to 1 atmosphere, which is equivalent to 760 mmHgs. At 25 degrees Celsius, the solubility of a certain gas in H2O is 0.75 grams per liter of H2O at a pressure of 1 atm. What is the solubility of the same gas at 10 atms of pressure? So we're given a temperature, we're given a solubility, and we're given a pressure. What is the solubility, S2, of the same gas at a pressure of 10 atms? So I know solubility. Now the units, grams per liter. Well, a liter is 1,000 grams. But if they give you units like this, go ahead and use them. Pressure 1 atm, that's at STP. The only problem is that 25 degrees Celsius puts us out of STP. But either way, this is our pressure. We're looking for the second solubility when the pressure goes up to 10 atms. Here's our Henry's law equation. We're going to plug in our numbers. This is grams per liter. This is atms. We would cross multiply the 10 across to solve for x. Final answer is 7.5 grams per liter. Now, if we wanted to, we could take this and actually convert. For every 1 liter, you have 1,000 milliliters, and the density of water holds true for every 1 milliliter. You have 1 gram. And you could convert into grams of solvent if you wanted to, but we don't have to in this problem.